broadcast sound. My name is John Wu, the left guy. I'm the presenter for today's broadcast. The right is the broadcast host and the keys. In the middle is the foreign form. He is the panelist. He will help to answer. Let's begin the presentation. Again, the title of my presentation is Simulating the Dynamic Muscle Force in an Index Finger During Typing. First, I want to thank my co-authors, Dr. An, Dr. Cutlip, Dr. Kleiniak, and Dr. Thom. Dr. An works in Mayo Clinic. All the other guys are my colleagues in National Institute for Occupational Safety and Health, now in Morgantown, West Virginia. In this work, I will demonstrate how to use antibody to solve practical clinical problems. It is well known through many epidemiological studies that excessive computer use will result in an increased risk of developing musculoskeletal disorder in the hand. It is well known computers are most common tools in long time, both at home or in occupational activities. And the computer use, where it is well known, are related many hand-arm musculoskeletal disease. On the experimental studies, especially EMG measurements evaluating muscle activity during typing, suggest that MSDs in hands are induced by excessive repetitive musculoskeletal loading. However, no biomechanical model in the hand have been developed to evaluate quantitatively how muscle force changing during the typing and how the force is shared in the different muscles during the typing. So in this study, we try to apply antibody software to develop a model in the hand to simulate the dynamic muscle force. Because experimental evaluation of dynamic loading in individual muscle in the hand during typing is technically very difficult if it is possible. Therefore, multi-body finger model have been developed to study such kind of problems. Traditionally, such a kind of model have been developed to study the dynamic contact and the joint movements, joint angle motions. However, none of these previous models have developed to evaluate the muscle force. One of the most promising theoretical approaches for exploring the musculoskeletal injury in finger during typing is to develop a theoretical biomechanical model. Such kind of model should contain muscle, tendons, and some detailed structure finger at least. In the literature, there are several models developed. For example, this Sanko Blue and his co-workers have developed a static gripping and a free movement model for the fingers. And the Broker developed the muscle force model, developed a finger model simulating muscle force in pinch grip and the distal rotation. And the biggest Hodge developed tendon muscle excursion models. But all these models are based on mathematical model simulations. They are not graphical based, so it is difficult to use this model to solve practical problems. Recently, Varela curves have developed a graphically based model. The model for their research group is very approximate. They are graphically based. They consider realistic tendon muscle connection or the musculoskeletal parameters. However, their model are not based on commercial software. So in this study, we try to develop our model based on the commercial software antibody, such that all other research can compare and evaluate this model. That's the beauty of this commercial software. So the objective of this current study is to analyze dynamic muscle force in an index finger during tapping using an universal finger model developed on a platform of the commercial software package antibody. So the index finger is modeled as a linkage system composed of 4 sections: the distal, middle, proximal, and the metacarpal flanges. The metacarpal flanges are fixed. All the other 3 sections are moved relative to metacarpal flange. There are 3 joints: the GIP, distal interphalangeal, and the PIP, proximal interphalangeal joints are modeled as hinges. They have only 1 degree of freedom, rotate only around 1 axis. The MCP is a metacarpal flange joint. The model as a universal joint. It has 2 degree of freedom. They can rotate in the axis on the 2 axes. They can rotate. However, in the during typing, even the MCP is rotate only around 1 axis. So finger model is include all the 7 major muscles. The muscle has attached the bone. The attachment locations, finger section dimensions are defined according to the well-known nominative model developed by Dr. An in 1979. So there are 7 muscles included in our model. There's FP, flexor profundus, on the FS, flexor sublimites, on the EI, extensor indicis, on the EC, extensor digitorum communis, on the RI, radial interosseous, on the UI, ulnar interosseous. RI, UI are symmetric around the center. On the there's LU lumbrical. This is on the side of UI. So let's look at the model. Bony sections are included in a model. These bony sections are obtained by micro CT scanner of the cadaver right hand and included in the model. Such kind of procedure nowadays become routine in the clinics. The model was developed on the platform antibody and written in any script code. It is antibody program language. We include all the muscle. 7 muscle are considered as heel type 3-element muscle, which consists of 1 contractile active element and an elastic element, which is parallel to that contractile element. And there is 1 serious elastic element, which simulates the tendon. So heel type 3-element model is virtually include a tendon. So we include a pronation angle and fiber length, and the remaining is a tendon. The recruitment of the muscle force is calculated using a minimum maximal optimization procedure in anybody, in which the maximal normalized force is minimized. In such a procedure is physiologically equivalent to the minimize the fatigue. So if you minimize the min max optimization, it is equivalent to minimize the fatigue in the procedure. The muscle parameter, including physiological cross-section area, PCSA, the optimal fiber length, and the pronation angle. All these parameters are taken from literature. Here shown is a nominative model proposed by an nominative model. All the dimensions are normalized to the section in the middle finger is O2, O3. This is normal 1. All the other dimensions is normalized to this one. So all the attachment location also dimensionless normalized to the O2, O3. So once you know dimension of a finger, then multiply real dimensions and all this attachment location or section length has a dimension. So this dimension is summarized by 8 or 10 cadaver specimens on the. There may be some difference if you use real models. And the dimension ratio may be a little different. However, in this model, we just demonstrate how muscle force changing change. We are not concerned of dimension. Therefore, all the other users want to interest in the real particular cases, then this ratio should be adjusted to fit the real cases. Even the standard geometry of bony section should be individually fitted. So in this study, we just consider typical cases. We look at how the force changing change. In this table, we show the attachment location. The X, Y, Z are local coordinates, which is defined in this coordinate. For example, in this section is a coordinate, local coordinate defined as here, the origin point. And this is defined as here. So across each joint, BIP, PIP, MCP, we have the tendon attached to two locations, as shown as this model. So for example, DIP, then there's one side a distal point, then another side a proximal point, then tendon, TE tendon, across this joint attached to one location, this coordinate, other location, this joint, this coordinate. Then across the PIP, there is 5 tendons, for example. They across this joint is 2 points across this joint. Then MCP has all 7 tendons, all 6 tendons across this. And there's 2 numbers. The number outside is actually number we used in our model, and the number in parentheses are original data measured by Dr. An in early study. We don't use this because we find use this in sometimes there's some conflict. We first calibrate our model compared to the tendon expression with the cadaver experimental data. Then we adjust this data slightly to fit this expression. Then finally we have the model. We simulate the typing. Then this number delta R is a difference between this actually used point compared with nominative model. You can see here in most cases there's no adjustment. Fit very nicely to the nominative model. In some cases there's some adjustment. For example, especially DIP joint in this particular point. There's some adjustment, but generally nominative model is very good to describe typical cases. So in order to simulate this finger, we have to consider the last moment of inertia, which has around 3 axes. That's Z, Y, or ZX on the Y, 3 axes. This ICZ is the mass moment inertia around this axis. ICYY is around this axis. The ICZ is around this axis. Here we can see here we consider tissue on the bone, we calculate separately. The bone is considered in the hollow in the center, but not go through. But it has a dimension, a cross-section elliptical. On the soft tissue is considered elliptical. Bone goes through it. Then we consider this all sub T is represented the tissue. Then if you have all these dimensions and put this in, then you will be able to calculate the mass moment ratio of each sector. And IXTT tissue plus IXTT bone, for example, is a total. The sum of this is a total mass moment ratio of that finger section. This table shows all these dimensions. The bone is external, has a dimension A, B, and the length is L. AB on the radial, elliptical radial in two directions. Then it's a distal, middle, proximal finger has a different dimension on the length. The bone canal is this hollow pool in the center of the bone has also dimension. All these data are obtained by literature. The tissue external has also measured. So use this data, we calculated the mass and the mass moment of inertia in all three directions. In the calculation, we use the soft tissue relative density as 1.0, which is quite logic, is reasonable. And the bone relative density is 1.9, which is average from the published data. So we will see here is this one axis actually is a predominant, which is larger, or which is smaller. This is X. X is axial. We look at the first figure. X axial. This is smaller. Or the other figure. You can see this is much smaller than the other two. This almost twice as this one. So these two IYY, ICZ are predominant. This figure shows all the muscle parameters we use in our calculation. Physiological cross-sectional area, fiber length, and penetration angle. All these data are also published in the literature. It's just collected, fit in our model. So this is our model. We put it together, then we have a model. The model is actually the numerical reconstruction of a finger. You have all the data, you have all the muscle characteristics, then you have all the inertial mass moment of in three directions of each finger section. Then attach the finger together, then put experimental data. Then you have the model, you can do the simulation. What's the input? How to model driven? Because it's the inverse dynamics. We input the joint angle as a function of time. Second is the contact force. Because it's inverse dynamics, it's impossible to do like finite element simulation in real contact, consider the tissue mechanical property. It is impossible. In this such kind of model, we can only use measure the contact force, input as a contact force. So the simulation prediction input is a history of typical impact force in the fingertip. The time history of DIP, PIP, MCP, joint angles, rolling piping. These data are published by Gingrich in 2004 in Journal Biomechanics. The model output is the time history of the joint torque on the muscle force. So we did in this study two kinds of simulation. First, we simulated the joint moment as a function of time. Just in the first stage, in order to calculate joint torque, we assume no muscle. The muscle is only all the muscle force is concentrated actually in the joint so-called joint muscle are applied. All three joints are constrained. Then the generalized joint action are considered as a joint torque as output. Secondly, we release this joint muscle, then replace them with actual real muscle model, that is three elements Hill's model. Then in this case, all the joint moment is carried by muscle. In a real joint, there is no joint moment actually. The moment is carried, balanced by all muscle. The sum of the muscle is back to the joint angle. This is called the joint moment. So in two stages simulation, then we obtain the joint moment and the muscle force as function of time. So this is what our data input. This first figure shows the force input. This is a measured force. We actually measure the force. And then is DIT as a function of time. The dot is experimental data is a curve. We fit smooth this data as user input. Then PIT on MCP. Then we calculated this joint angular velocity and the angular acceleration. So I will first show you the model, how the model looks like. Here I show the model. Here is I have calculated all the results there. I want to just show you the structure of the model, how it looks like. All these bone sections are scanned, the input. We first look at the there's a modular. The model is there's main program. There's a modular. There's a main program very short. It's like C++ or Fortran program. We call a subroutine. Then you calculate some detail. The first including is the index parameter. And in here we input all the parameters. Most of the data are found in the nominative model developed by Dr. N in early years. Then we input middle finger length here, then normalize all these ones. Then you can see here is maximum moment inertial data is input. Second section is the metacable. This section is fixed, is not much to see. There is only coordinate defined where the muscles are attached. Muscle attached, the one end is the distal side of the metacable. Then this index section defines all other three sections. For example, I show you how the mesh single mesh is input here. This file defines the single mesh. It is scanned, micro CT scanned. Then we put it in this side, then include it. Then through several algorithms, you can rotate parallel moving this figure then to match your model, and also scale to the exact size of your model. Then all the other statement is virtually this define the attachment location of each muscle. Then this joint very, very simple. There is only three joints. We have only three statements. Is a universal joint, revolve joint is a hinge, revolve joint DIP. Very simple. Then this muscle is quite a lot of data. First, you have input the muscle cross-sectional area on the muscle fiber length and the pernicious angle. Pernicious angle, this is in degrees. Then the index force, which is input on the contact force, is collected from the published data as input here is a file. Also, this joint driven by measured data as a function of time, three files, DIP, PIP, and CP. Then we have the results. After simulation, we have results. I show you how the results look like. All the results here. This is all the muscle. Here is the muscle length changing as a function of time. This is the typing force. This is second. This total time is only a little more than 200 about 50 milliseconds. This is the FP force, then FS force. Then this EC muscle is activated before and after contact. And EI muscle, on all the muscle force is here. Let's continue the presentation. Next slide shows the joint moment as a function of time predicted compared with the published data. This is not measured, is also simulated. We just make sure it's consistent with the published analysis. This first dotted line shows the beginning of contact, last is the end of contact. Then we'll see DIP, PIP, MCP, joint torque as a function of time. Fits very well to other people's published data. And the right column shows the stiffness of the joint. That is joint torque as a function of the joint angle. Again, we see this data, simulated data is agree well with other people's model in training. All three joints, DIP, PIP, and MCP joint fits very well. So this is a final result figure. We can see here is FP muscle force and FCP are two predominant. Compared to the maximal force at the fingertip, the ratio of FC muscle is about 0.95, for FP muscle about 2.9. This data we compare to the published experimental data. Most people study FPFS muscle during the static clicking or typing. They find that in this range, they agree very well. So the UI and LI muscle also activated during the typing. Interestingly, there's three muscles. They are not activated during typing, but before and after typing. Secondly, we compare our experimental results with the EMG measurements. In the recent paper, Core 2006, in Journal of Biomechanics, they published the EMG measurements in different muscles. RI, UI, these two muscles are virtually symmetric around the center. So they are activated during this range. You can see here, there are four muscles. This four muscles are activated during this range. These two muscles is consistent with our theoretical prediction. They are activated during this. There are two muscles, EI, EC. They are also symmetric on the top of the finger. They are activated well before and well after the activation, the typing activity. There's these two muscles. They are before and after typing. Again, they are consistent with the EMG measurements. Only one muscle which are not consistent with the prediction is LU muscle. According to our simulation, this muscle should carry force before and after the activation. However, in EMG measurements, they are same time as this small muscle. But however you look at the magnitude of this LU muscle are very small actually compared to other muscles. See, the force in this LU muscle could be considered as negligible in this small number. So we know this even activated muscle not necessarily carry load. So the simulations are not inconsistent with experimental data. So it's also pretty good consistent with experimental data. One interesting thing I will show you is I marked here is the beginning of contact. All the EMG data was seen well before the contact. Before you apply the force, the muscle is already activated. However, in the measurement, in the force measure, we will see only after contact, muscle carry the force. So this is very consistent with many people's observation. EMG data are usually go ahead of the force. Also, you activate the muscle, you apply the electrical stimuli, the force always follows the stimuli. So discussion. In this study, we predicted the maximal peak force in stress on FT tendons are consistent with recent experimental data published by Kreuzer 2005, but much smaller than early experimental data published by Hewing 92 on the Denali in 1999. The predicted time sequence muscle loading is consistent with EMG measurements. The recent paper in Core 2006. Our simulation results suggested that the muscle force in the finger during typing are mainly induced by impact force at the fingertip, not due to the mass inertial effect of finger flexion. As we have tested, we have changed the mass moment of inertia from very small to very large. We find the mass moment of inertia has effects compared to fingertip typing force is very small. So there's one point I will discuss with you. There's some limitation of this model, especially to simulate the tendon network. We know in a tendon, in the finger, the tendon network is very complicated. We have simulated this net use approximation. For example, in this net, especially difficult is one tendon on the branch in the toe, then attach the two locations. So it's a very complicated to simulate in anybody as inverse dynamics. So theoretically, if one tendon there has three branches, if you want to simulate strictly, you have to apply a massless floating body. Then the main tendon attached to this location, then three other tendons branched. And when apply the force, then this free body will find its balance location, equivalent balance location. However, in anybody, is inverse dynamics method that cannot be performed, because in inverse dynamics, each body has to be specified, defined this locomotion as a function of time. So we don't know when it is equilibrium, how it is located, where it is located. So we need actually forward dynamics to simulate this more exactly this tendon connect network. So in this present work, we have approximated this problem using a Y point which is fixed on the bone. Then This tendon branch simulated with 3 tendons go through this point. So the total force carried by this muscle is the sum of all these 3. So the displacement or expression of this muscle is the average of these 3. As long as if during the locomotion, the elongation or expression of these 3 muscles is not changing much, then this method is a pretty good approximation. So this work I just presented is published in the recent issue in Journal of Biomechanics. You can find this journal in the online. Thank you for your attention. Now I'm ready to answer your questions.